Okay, so this is a separate recording of this particular part of the lecture. There'll be two recordings for today at least. So video display technology is an overview, a couple of quick definitions that we'll be talking about. One is response time, and response time in a monitor is the speed that an individual pixel can change on or off or from one color to another, which is different from refresh rate. And refresh rate is the number of times the entire display draws an entire frame, right? Or draws the data being given. That's kind of a fancy way to put it. Another one is backlight. So a backlight is a rear mounted display light source. And what a lot of people don't realize is that monitors like the ones you're looking at right now in your laptops and phones have a light behind the panel. And that is considered to be external to the source. So it's confusing because some people think, well, it's not external, it's inside the lid, or it's all one piece with the panel. Yes, it is. But what that means external to the source is that the imaging portion of your screen is not generating any light. There's a light behind the imaging portion, and we'll talk about that today. We'll get into that. So I just wanted to give you a quick idea of the definition. So the backlight is that light source behind the imaging portion of the screen. All right. The downside to backlighting is that it contributes to things like lowered contrast ratios, uh, which is not desirable. So let's talk about contrast then too. So contrast is the difference between the brightest and darkest parts of the image. It's a bit like dynamic range in a way. It's one measurement of the monitor's ability to, pardon me, contrast ratio is one measurement of the display's ability to render contrast. A higher number is better. So if you want a contrast ratio of say 10,000 to 1, it means you've got 10,000 units of brightness to 1 unit, right? As opposed to 1,000 to 1, which means it just doesn't have the range, isn't as bright. So when you see a contrast ratio, and I shouldn't say bright, it isn't as contrasty if it's a lower number, all right? So a higher number is better when it comes to contrast ratio. And again, the contrast ratio is between the brightest part of the picture and the darkest part. So it makes sense that you want the brightest part to be as bright as possible and the darkest part to be as close to zero, which is absolute darkness, as possible. So they use 1 in the ratio because there's no ratios that really can work with 0, right? So what are video displays? TVs, scoreboards, mobile devices, computers, signs, right? These are all video displays. How are they different from a video monitor? Well, a video monitor is something that you use to measure with. And the dictionary says that it's an instrument for use for observing, checking, or keeping a continuous record of a product, process, or quantity. So I use the word monitor very carefully because when you're in the professional realm, a monitor means something. You cannot use them interchangeably to say a TV is a monitor, although people will say a TV monitor. And it's really only depending on its use and its quality. If you're using a monitor to do any kind of quality assurance, then you have to make sure that the monitor is accurate. We'll talk a bit about that today. All right. Yeah, so I just kind of reprised this. A TV is just used to watch or view. You're not that critical when you're watching or viewing something. You just kind of watch the content. Not all displays are monitors. You know, like scoreboards in an arena is not a monitor, and not all monitors are displays, right? And then just to confuse people, in audio, monitors refer to speakers or headphones because they serve the same purpose as video monitors, and that is that they're there to evaluate, right? So they have to have a very accurate profile. So you will hear audio people refer to monitors when they mean, you know, speakers and headphones. So you sometimes have to be clear on the set what you mean. So it's all about context. If a director says, I want a monitor to look at something, you know it's a TV video monitor. If the sound person says, you know, I need a better monitor, then they might need a speaker. You may want to ask, do you mean a speaker or a TV? That's just the confusions of the language, all right? So what do we want out of a screen? Well, we want a screen we can trust, right? So it's got to be easy to see, easy to use. You don't want to have a complicated remote and a bunch of complicated controls. Most professional monitors avoid this. The cheap ones, and you'll see this as well with cameras too, the cheaper the product, the more menu driven it is. You want a sharp image and you want a proper size. And proper size is appropriate size. You don't want to give a director a 21-inch or 42-inch flat panel display when all they want to have is a little 8-inch display just for framing, right? And you don't want something that's gigantic, because the other thing, remember, with a director's monitor, they have to be able to see around the monitor to look at the actors. So you don't want to block their view of the giant panel. So when you're a professional, you also want it to have an accurate image. You want the color to be accurate, and you want an accurate aspect ratio. I say that last one because a lot of computers are 16 by 10, and a lot of computer monitors are 16 by 10, but 16 by 9 is the aspect ratio of video. So you got to be careful, because if you throw a computer monitor in as a monitor, it may stretch the image to fit that. It might do what's called a fit to fill. So you want a dot for dot. Whenever you go to a monitor settings, you want to make sure that as a professional, that the aspect ratio is not being zoomed or stretched, right? So I'm going to end this for a second. We're going to go to a quick stop share. Now I'll have a quick look at displays. I want to do a quick recap on scanning. And I'm going to skip ahead way down. So this is a slow-mo, guys. Here we go. They got a flat panel display. They're going to point a camera at it. But first, we're going to look at this. Hang on, I've got too far. So remember this. This is slow motion of a monitor, or in this case, a TV. And this is how the scanning works on every TV.
It takes an extremely fast camera to see that each frame is built line by line from top to bottom.
Digital or analog, right?
It takes an even faster camera to see that each line
is
drawn from left to right. Slow down to 28,500.
So you can see that this is how your monitor is building up an image. And there's only, if you'll notice, there's only one bright spot, one line of pixels being lit up at a time. But the persistence of vision of your eye creates the entire frame in your head. I'll let that sink in for a second. So it's not like you're painting a wall where as you paint down the wall, the paint at the top stays there. In a display, as you draw these lines down the screen, the lines at the top start to go dark. But it's all happening so quickly, you don't notice that. That's the key of the frame rate, right? The only reason the technology works is because our eyes will hold the image that they've been flashed for a moment, long enough, and that moment is long enough, 1/24 of a second or so, for us to build up an entire picture line by line.
100 frames a second, we're now seeing glimpses of that, but we do need to go even slower. This is now 118,000 frames a second. I'm going to put the stats up for you here, so you can see the actual amount of time that it took. And you can see now that the line is being drawn from left to right on the screen. Now at 146,000 frames a second. To gain perspective on just how slow this actually is, you can see the exact time I shot this.
So some of you are probably saying, well, how come I can see more than one line on the screen? Well, that's because the other thing that screens have built in is they have their own little bit of persistence. The material the screens are made out of allows the previous handful of lines to remain kind of faded as they fade out slowly. They don't go black immediately. So that aids our brain and aids our eyes in seeing a smooth single frame put together.
All right. So this is hours. It was just past midnight, 23 minutes, 41 seconds. This is a 1/10 of a second, 100th of a second, 1,000th of a second, or a millisecond. And then over here, you've got a 10,000th of a second, 100,000th of a second. And this unit here is the millionth of a second, or a microsecond. We are now at 380,000 frames a second as our recording frame rate. That is the highest frame rate we've ever shot so far on this channel. And
so now you can start to see the individual pixels. They've slowed it down to 300,000 frames per second, which is a stunning number to me. And you can see the individual pixels appearing, all right?
Using this information, here's a little bonus fact. A CRT screen can draw Mario's mustache in less than a 380,000th of a second. That is some seriously fast facial hair.
So what he's shooting here, by the way, is an old-fashioned CRT. This is not a flat panel television set that we use today. That comes later in the video. And so the nugget I want to stop and mention is that he mentioned that mustache on Mario, this is a Mario game that's being scanned, is being drawn in less than 300,000th of a second. So that's an important thing, because the old-fashioned CRT TVs were very fast. And so this is one of the challenges when we went digital, and we're still fighting it today, is that CRTs had two big advantages over everything that's come along since then, up until recently: high contrast ratio and very fast redraw speeds. And the third thing that CRTs had that nobody really talked about was that CRTs didn't have a native resolution. If you could create an image that moved that electron beam, it would change the resolution to anything. We never did that back in the day because there wasn't any need for it except for military applications. But CRTs, because they're built at the molecular level out of materials that are molecular sized, uh, which sounds amazing when you think about how long ago it was, almost 100 years that the CRT has been around. It had no native resolution, which made it very flexible for things like this. Anyway, moving forward now, we're going to move into the pixel. So let's go to the flat panel screen, which is later in this video, and have a quick look at, there we are. So what you're seeing here, now we're not in slow-mo anymore, now we're super close. So what you're seeing here is a flat panel. If you look up at the top corner, you see him with the camera on the tripod. Everyone can see that, I hope. The flat panel screen. And these are the subpixels, the red, green, and blue subpixels that make up individual pixels. Now you see those little tiny wires? So those wires, those little black lines in the front and the little squares, that's all part of the electronics that makes the image work. Those wires are there. They are that visible, that close. It's just as you step away from the screen, even just a distance of your finger from your screen, your eyes no longer see those wires and they blend into the background. Some technologies nowadays are using clear material for wire, and so it makes it even less visible. All right, so let's just have a look at this up close.
We're now looking at the subpixel level. A pixel is made up of 3 subpixels: red, green, and blue, RGB. You may have heard that before. And this creates the illusion of different colors. By dimming and brightening different subpixels to different intensities, this screen can create the illusion.
Okay, so you guys see on the left, the screen is now green. This is how the green happens. You'll notice there's only green subpixels lit, right? So each one of those green on the right subpixels is part of a group of 3. You can see that the blue one in the middle has a little bit of energy. There's a little bit of blue on the right-hand side you can see between the green ones, but it's not, I'm not quite sure why that's happening. It should be all green. It may be that the color they chose for this experiment isn't a pure green. It might have a little bit of blue in it.
Of literally millions of different colors.
So now as they change the color on the screen, you'll see the blue, and so that's exactly what it is.
Dim, you go through gray all the way down to black. So if green dims away and red and blue are still lit, then you go into magenta, purple, that sort of area, and that's how the colors are made. So every time on your TV, you're looking at a white image, you're looking at tons of blue, green, and red lights. They're just so small.
So again, just to help puncture the illusion, you'll notice the camera's pointing at a white part of the frame. It looks white, right? But when you zoom in, it's just that all 3 subpixels are lit. And when those RGB subpixels are lit together, you get white. So this is an illustration of that, okay?
They look like white to your eye. Before you get white, red, green, and blue blurs into yellow, cyan, and magenta. And that's what happens here when I move the screen slightly out of focus. This is too close to watch a slow-mo guy's video. I might vomit. It's the same situation, just entire blocks, and they're bigger.
So this is an analog CRT screen. Now you'll notice that it also has subpixels, but these subpixels are a little different. They're not individual discrete elements. They're in fact just what's called a mask. The electron beam is changing color as it passes across the screen, but we don't have to get into that detail today.
As I mentioned before, this is a 4K LCD screen, which a while back were typically lit by CCFLs or a cold cathode.
Okay, so I'm not going to let him get into that because we'll talk about that next. Anyway, so that's that. Stop share. And yes, does it take, the question in the chat, does it take more electrons to make it white? Yes, it does. That's one of the downsides. Well, I don't know if it's a downside. If you're into efficiency, the more white on a screen, the more energy it takes because all the pixels are lit all the time. So yes, it does take more energy to make it white. And so this is a way they cheat, by the way, with phones and laptops, is they'll often dim the screen to save energy, right? And the dimming the screen just reduces the amount of white as well as everything else, of course. Okay, so back to our presentation. Bump, bump. Okay, share. Play from here. Okay, so now we've seen a little bit about how the pixels are put together. Just keep in mind that a pro doesn't just eyeball an image. A pro needs to know for sure that things are the same, because remember, I'd like to sort of use the analogy that we're scientists of video. And so a scientist wants to make sure that whatever experiment that they've just done, they can do again. There's a classic saying, I think Ricky Gervais said it years ago, about if you burned all of the science books on Earth, in 1,000 years, they would all come back exactly the same, because all the experiments that you would do in that meantime would have the same results as they did the first time around, right? And that's because when you do science, and what we do when we do technology for video and film is we are doing science, we're playing with electrons and all this other stuff. You've got to make sure you can reproduce whatever you've done on command. If somebody says, I want that field, like we're using this slide here, there's someone in a field, I want that same sky in my next shot. Well, you've got to know how you got the sky in this shot, and then be able to apply that lesson to the next shot. So you're really doing an experiment in a way. You develop a look, and then someone says, okay, now make that look again. And a pro can do that. An amateur is like, give me a couple of days and I'll come back and figure out how I did it. And then they'll do the experiment and figure it out, right? So you don't just eyeball stuff. You want to know and make measurements and make notes, right, at all times, if that's your avenue. Okay, specific attributes in a display. We want things like, these are desirable attributes. We want high resolution, high brightness. We want a large viewing angle, which means you don't have to sit right in the front of it to look at it. And that's an issue we'll talk about in a second. You want high writing speeds, which means you want the screen to refresh and the pixels to refresh quickly. You want a large color gamut. You want all the possible colors you can get. You want it to be cheap. Good luck with that. But you want high contrast. You want lightweight and low power consumption. These are all the ideal features of a display. They're not all possible, right? For example, you can get probably all of these on a screen except the low cost. If you pay if you pay a fortune, for example, with micro LEDs right now, they're enormously expensive, but they do meet a lot of these qualifications, right? So you're paying for it in cost. So some existing display technologies. Here's two columns on the left and the right. Generates its own light. So remember what I said before, the imaging portion of the screen on LEDs does not generate its own light. But the imaging portion of a cathode ray tube, an old style TV, a plasma TV, which I happen to have actually here at home, an organic light emitting diode, and possibly, not yet, quantum dots, will generate light from the portion that is in fact the image. All right. And as I said, if this confuses you a bit, don't worry, we'll go through some of this. Things that need an external light source, external to the imaging portion, are DLP projector displays that are used in theaters, liquid crystal displays, which have various backlights like CCFLs, as he was about to mention in the video, LEDs and quantum dot filtering, right? These all use different methods to massage the light coming from an external source to the image. So, you know what, I'm going to skip ahead a bit because I'm talking about this thing and you should kind of see. So I'm going to go to the sandwich portion. We'll go to the sandwich portion of our lesson, and we'll talk about what screens are made out of. So if we look at an LCD, for example, an LCD is made up of layers. This is a cutaway view of an LCD pixel. And you can see that there's a polarizer at the bottom. There's a substrate, which is a liquid crystal. There's a substrate underneath that. There's a liquid crystal in the middle, which is that shown by that gap. And then there's a filter on the top and a polarizer on top. It's a sandwich. A plasma TV is basically a bunch of little containers full of gas that are then sandwiched between layers of glass like this. So you've got these little containers full of gas and these glass elements on either side of it, right, that make little compartments. But they're all layered together like a sandwich. Here's another example of a plasma TV. Here's an example of, we'll get to the Swiss cheese, don't worry. Here's an OLED. So an OLED has a glass plate at the back, and it's got organic material in the center. It's all squished together, right? That's my whole point. It's all sandwiched together. Well, one of those sandwiches in an LED, and we'll talk about that now, we'll show the video, is in fact a light. All right, so I'm gonna skip this. I've already talked about this. You know what? Okay, hold that thought about the LED. I'm going to go through a quick survey of display technologies. Cathode ray tube, also known as the old TV set. It's a 100-year-old workhorse. It's got a good color gamut, best performance to cost, bulky, heavy, heavy, heavy. You know, they weighed kilograms, many kilograms. They're obsolete. They generate their own light. They had high res, high brightness, large viewing angle, and they were what's called a beam scan device because an electron beam created the image, and the electron beam also created the light. LCDs, these are the most common, what they call the most mature, which means it's been in the market the longest time and it's most widely used. It's got a poor viewing angle. It doesn't generate its own light, but it's cheap and has a bunch of other attributes. It has slow write speeds. It's inefficient compared to other displays. It's affected by temperature and sunlight, but it is cheap and cheap to make. So that's why they're so ubiquitous. They're everywhere because of the cost, right? And because they were early, let's not forget they were an early technology. DLP projectors, digital light projectors, or also called digital cinema projectors. These use gigantic lamps like xenon and halon, xenon and halogen lamping to get extremely high light levels, which you need for a theater. They're super bright. They don't generate their own light because of the lamp. You can see here, this one has a vent fan coming out of it because it is so hot because of the lamp. It's very complicated. There's lots of moving parts. For example, every pixel gets a mirror. So you can imagine if you've got 1 million pixels on the screen, there's literally 1 million mirrors inside this device and they all move. There's a color wheel that makes the colors happen. They're quite complex. So as a result, nothing that we'd probably ever deal with on our own. These are different, by the way, than the projectors you're going to see everywhere else, like the projectors in classrooms and such. Those are basically just LCD screens like these, except the backlight is super bright and then it's pushed through a lens and focused, right? So it runs the same as liquid crystal, most other projectors, but the DLP projector is specific because it's high quality, high brightness. Then there's OLEDs, organic LEDs, and these have no backlight. These have their own light generation. They have a very high redraw speed, and they're 1,000 times faster than an LCD. They have a thin form factor. Organic, not really. They use organic chemistry, but the things aren't really alive. It's not really organic. And then micro LEDs, which is the same as an LED, only smaller. So that's the quick survey. We'll get to quantum dot. That's the quick survey. Let's just go to stop share the video now and explain what the LCD, hang on, I'm not ready yet, don't share, haven't queued it up. Explain what, here we go. How the LCD works.
Lehmann and Reinitzer.
So this is put together by Sharp. I'm just going to share it now. It's a bit dated, but it's still accurate.
Lehmann and Reinitzer. LCD technology from Sharp. Today's modern LCD technology is based on a discovery made by engineers Lehmann and Reinitzer around 120 years ago. In their research work, they came across liquids with typical crystalline properties. This is how the term liquid crystal was coined. Let's take a look at the technology in detail. In liquid crystals, the molecules are similar to long, drawn-out rods. As with crystalline structures, these molecules exhibit a strictly ordered crystal structure. The ordering of the molecules creates a directional orientation. In most LCD displays, the liquid crystals are embedded between two glass plates rotated by 90 degrees. This formation produces what is known as a twisted nematic LCD. A polarization filter is fitted onto each of the outer glass plates. These polarization filters mean that only one dispersion direction of multiple light waves emanating from a light source is allowed to pass through. The light follows the rotation of the molecules and, twisted by 90 degrees, hits the outer polarization filter. As the rotation means that the direction of the light matches that of the polarization filter, the light can also pass through this filter and brightens the outer glass plate at that point.
Okay, so I normally stop at this stage because it could be a lot to absorb. So what's happening here, besides the fact that they seem to be in love with Lehmann and Reinitzer, who discovered this theory, is that you've got two glass plates. This is an LCD display, like the one you're probably looking at now. If it's not an LCD, then don't worry. You've got two glass plates, and in the middle, you have a liquid crystal. What's important about it being liquid is that crystals are generally rigid, right? Crystals like diamonds, glass, well, glass is a crystalline material, but diamonds, quartz, things you can think of as crystals are typically rigid. But liquid crystals are cool because they act like they're rigid in the sense that they do the same things optically and visually that a crystal will do, but it's a liquid. So in fact, it can be moved. And the trick with that is you then take these two pieces of glass, you put this liquid in the center, which is shown by what I call the hot dogs in the middle. And these hot dog molecules can then be twisted. And then by twisting them, you can make them do things that you wouldn't normally get. So for example, if you just took two plates of glass and put liquid crystal between it and shone a light between the two pieces of glass and the crystal, like the three layers. And you know, this is so weird. This is the problem with this. Hang on, let me stop sharing. Let me just go to the screen. So if you took, two pieces of glass and put liquid crystal in the center, right? And shone a light through the two pieces of glass and the liquid crystal, the light would pass all the way through it. So it acts like a crystal. What they do with liquid crystals is because liquid crystals have another feature that's interesting, is that not only are they like crystals, but they're also electrically active. So if you took that two pieces of glass and you put the liquid between it and then you twisted one piece of glass 90 degrees, I guess I can't. If you took the two pieces of glass and you sandwiched them together, and then you twisted one piece of glass 90 degrees, you also, by pressing the two pieces together, you're twisting the liquid. So it is now twisted. The molecules are twisted. And that's what the video is showing you, right? So I'm going to go back and share. We'll pick it up here. So now you've taken the two pieces of glass.
Rotated by 90 degrees. This formation produces what is known as a twisted pneumatic LCD.
So sometimes called a TN panel, by the way.
A polarization filter is fitted onto each of the outer glass plates. These polarization filters mean that only one dispersion direction of multiple light waves emanating from a light source is allowed to pass through.
Wow, that's a lot of stuff to digest. Okay, so I'll show a quick video about polarizing in just a second. But what polarizing does, for those that aren't aware, is it takes all the light rays that are coming at the filter, in the case of polarizing sunglasses, they're coming at your sunglasses, and it only allows through light waves that are traveling in a certain direction, that are vibrating, I should say, not traveling. They're vibrating in a certain direction. So light waves, as they travel, they vibrate. And again, you see, I need to use my hands here. So let me stop share. Light waves, when they travel, they vibrate like a skipping rope. So if you can imagine a skipping rope, when you spin it, the rope is not only moving up and down and left and right, but it's also spinning in all directions. And at the same time, it's also the wave that you create by skipping one end is traveling down to the other end of the rope, right? So all this is happening at once with light. It's not just traveling at you like a bullet, which is often the illusion. We get this idea that things are traveling straight at you. They're traveling at you, but they're traveling in this kind of vibrating pattern that I'm doing with my hands here. So what a polarizer does is it creates a screen, if you will, of lines. And these lines then take the light that's traveling in all directions and only let the light through that's traveling like this. So even though my hand is moving like this in all directions, when I try to push it through the filter, only that comes through. The rest of the light that's traveling in all these other ways doesn't happen. doesn't come through the filter, right? So now at the other side of the filter, you've got light that's only going like this. It's still traveling forward, but it's only vibrating side to side. Okay. Why is that important? Because, well, now you've got light, you have a predictable flat beam, if you will, of light. For sunglasses, what that does for you in the polarizing sunglasses is it basically eliminates all the other light. So it just reduces the light level. And so when you put polarizing sunglasses on, it reduces the light level. And so therefore it's easier on your eyes. You're still seeing a pretty clear image because you have enough information in the light that's coming through to see, but it's way dimmer than if it was just simply unfiltered. There's other ways to filter light. Doesn't involve polarizing, simply darkening, like sunglasses that are merely just colored and darken the light or darken the image. But the idea behind a polarizing filter is it doesn't change the color of the light passing through it. Right. So many other kinds of eyeglasses, and I'll keep using eyeglasses because people can relate to this. A lot of sunglasses simply reduce the amount of light by adding color. Sometimes that color is a gray or a blue or whatever. And that colors the light that passes through, but a polarizer merely filters. It's like a strainer, right? So white light is still coming through. It's not now green or red or tinted. It's just only traveling in one direction, all right? So let's go back and share and get into this. So.
The light follows the rotation of the molecules and twisted by 90 degrees hits the outer polarization filter. As the rotation means that the direction of the light matches that of the polarization filter.
Okay, so what's happened now, we have this light that's come through in a flat way. And again, I'm using these terms very loosely because it's not actually that way, but imagine that it is. You're getting a flat beam of light that comes through and you've got a flat filter at the other end that's attached to the glass that you've twisted. And the flat filter is at 90 degrees to the first filter, but the crystals are twisted 90 degrees and the light travels along the filter, or along the crystal. Let's try that again. It passes through the first filter, is turned into light that's just flat. It travels through the crystals as though they weren't twisted. Remember when I said before that if you twist the crystal in a liquid crystal, it acts like a regular crystal. And that means it'll also transmit light like regular crystals do. And so you twist this liquid. By twisting the liquid, which you can't do with a solid crystal, the light will still travel through it because the crystals line up so the light can travel on a path, right? The light needs something to travel through and the crystal is the thing that it travels through. It then reaches the other side of the filter of the crystal. Oh man. It reaches the other side of the crystal and hits another filter. And this filter is in exactly the right alignment to let the light pass through it. Right? So as it does here,
filter,
bang.
The light can also pass through this.
So in a twisted pneumatic LCD screen, when you twist the glass and push light through it, it lights up that pixel, right? So how does this make a monitor work?
Filter and brightens the outer glass
Here's
plate
how.
at that point. If an electrical field is then generated between the glass plates, the special property of the liquid crystal molecule becomes fully apparent. As the molecules are dipolar, they react to the electrical field and are repelled. The rotated molecules.
Boom. So I wanted to let that play out because he does say something interesting there. These are dipolar. They're like magnets. They have a north and a south, right? So like a magnet, if you electrify a magnetic field or a magnet, it will shift either towards or away, right? So if that magnetic field around this pixel has a north at the top and a south at the bottom, the liquid crystals will move, and in this case, in a random way, because we don't know which crystal is oriented which way. We never did know this. They'll move to line up properly with that magnetic field. The problem with that is, and I don't say it's a problem, is that now they're no longer in alignment for the light to travel through. They've lined up for a different reason. The original lineup of the crystals was because we twisted the glass and they followed each other like they would. But the moment you apply electrical field, that breaks that pattern, right? Now what happens when we put the light through it?
Is interrupted. When light then passes through the first polarization filter and follows the direction of the molecules,
So you'll notice that the light travels through the crystals, but now it no longer follows the crystals properly. It follows the crystals with their new orientation, which is random, right? It's not a linear pattern like we had before. If we go back in the video to here, whereas the light was traveling from crystal to crystal because they
Molecules and
all
twisted by 90 degrees.
they were
hits
all
the
following a predictable curve. Now we have a bunch of randomly distributed crystals, and so the light, oh, let's get to it. The light, when it travels through the crystals,
direction of the molecules. This hits the outer polarization filter.
the light doesn't get bent. It stays in the original line of travel because light travels in a straight line. So the crystals are no longer there to guide the light. They're out of the way and they're in the wrong order. So when it hits the filter at the other end, which is oriented up and down instead of left and right,
and cannot pass through it.
this left and right oriented light won't pass through that filter. And now the pixel's black. So that's a long way of telling you that when you turn on the power to an LCD pixel, it shuts off the light, right? So an LCD crystal, when you leave it naturally, you twist the two pieces of glass with the crystal in the middle, light will pass through it normally. Electrify that pixel, turn on power, and those crystals will reorient, and all of a sudden, bang, the light won't pass through it anymore. I'm going to stop here because normally with a live audience, that's a lot to absorb. And I will even, I'll leave the recording. So questions about that? Oh, I see in the chat here. Is that a piezoelectric effect? No. Wait a minute. I say no too hastily. That's a good question. The piezoelectric effect is typically the other way around. Whereas if you move a crystal, it will generate electricity. So there's a lot of microphones, for example, that use the piezoelectric effect. You twist the crystal with the diaphragm of the microphone and it generates power. I'm not sure if generating power to move a crystal is the piezoelectric effect in reverse. That's a good question. Any other questions about LCDs and panels and stuff before I move on? It's a lot, I know, and it's difficult to do when you're not live. You can watch these videos. I'll put together a better playlist. There's one there now, but it's, well, in fact, no, what, you know what, there's a playlist in Learning Hub. Follow that. And it should be in the right order, actually, as we're talking about this stuff. The important takeaway is, first off, LCDs use a crystal. LCDs are layers. So there's a light behind the crystals. There's a layer of light, there's a layer of glass, of polarizing filter, there's a layer of glass, there's a layer of crystal, there's another layer of polarizing filter and glass. That is an LCD panel sandwich. We'll get into that detail a bit more this morning. The other important thing is when the power is off on an LCD pixel, there's no light. Sorry, when the power is off on an LCD crystal, it allows light to pass through it. When you turn on the power to an LCD crystal, it blocks the light because it moves the crystals out of their orientation. So when you twist the crystals, they retain the orientation that allows light to pass through them. When you apply power, it randomizes those crystals and the light no longer has a proper path out. And that's what blocks the light in an LCD panel. Okay. So
like, what's the takeaway? Like, what do you want us to, is this just so we have knowledge about screens?
Yes, because you've got to make, so if you want the ultimate, why are we learning this? And that's a good question. I always ask students to ask me what's relevant about this and what's the point. The point is this: you've got to be able to decide, and we're only talking about one technology at the moment. We'll talk about more later. This one's the most sort of complicated because it actually has physical moving parts. Those crystals actually physically move. But you have to be able to decide what monitor to use and what monitor to buy, right? And in order to understand what monitor to use and buy, you've got to understand how they work to some degree. I spend the most time in this lecture on the LCD because it is the most complicated. We don't get into the physics of all the other ones because it's really not important. What's important about an LCD is a couple of things, and maybe I could recap it. First off, there's an external light source, right? Which means there's a light behind the panel that is not made by the panel, it's made by a separate lamp. And we'll get into that in a minute about what kind of lamps, but there's different kinds of lamps. Problem number one with the light source is if you have a cheap panel and the light source is always on, which was the early LCD panels, then no pixel is ever totally black because light will leak through those pixels. So that's a bit of a drag. So your contrast ratio is low. There's moving parts, physically moving molecules inside an LCD panel. When you apply power, those crystals physically have to move. That takes time, right? And physically moving things is slower than moving things electrically. In other words, when you move electrons, they move way faster than when you move matter. And liquid crystals are literally matter. It's actually a liquid. If you ever break a liquid crystal panel, liquid will come out. Well, that liquid has to be physically moved by the crystals, right? All that has to happen. In other panel technologies, there's nothing, you're not moving anything, and therefore they're quicker, right? So that's kind of that. And then there's the polarizing. The reason we talk about polarizing a little bit is because that's what contributes to poor viewing angles. When you have a polarizing filter on something, the light comes out, remember what I said, it comes out oriented a certain way. Well, if you get too far off one side or the other of a monitor, that light that's moving a certain way doesn't get to you. So anybody who's ever seen an LCD monitor, or even any TV set, if you start to walk across the room and look at the TV as you're walking, you'll notice that it gets darker. That panel then has polarizers in it. It's probably an LCD panel. So if you're designing a monitor for Video Village and you need 3 or 4 people to be standing around it, they've either all got to stand one behind the other or use a different technology, like an OLED, for example, where there is no polarizer, or you use a micro LED or some other technology, or a CRT. There's all kinds of technology you can use. I mean, CRT, you know, forget that's dated. So it allows you to choose, right? That's kind of what you're learning. Questions, comments? I hope that's helpful. And, you know, I'm actually in the process of always reviewing this material. So I'm always open to students say to me, you know what, this doesn't make any sense in today's world. There's a couple of things we've stopped. For example, 3D. 8 or 9 years ago, 3D TVs were a big deal. And so we students actually asked me, could you include 3D in the lecture? Well, I did that for about a year or two. And then about, well, a year or two later, students said, why are we talking about 3D? No one's buying those, right? So that's kind of the way technology works. Especially there's fads and all kinds of stuff, right? HDR might be a fad. We talk about HDR for a while, and then a year or two from now, it's people say, you know what, HDR is no longer a thing. We don't know, right? There's always all kinds of fads coming along. So
What about like virtual reality goggles, like those little screens right by your eyes?
well, yeah, I mean, that's something else. Virtual reality is a great thing. One of the first things they discovered when they developed it was that lots of people vomit, and I'm one of them. I'm motion sick, so virtual reality doesn't work for me very well because it doesn't give me the signals to my ears. You know, you don't get that correlation between what you're seeing and what you're feeling, so it can make some people quite nauseous, and I'm one of those folks. And so when that kind of thing comes out, and you realize that part of your population is going to vomit whenever they use your stuff, it becomes a niche product, right? Because now only some people can use it, not everyone. So, you know, virtual reality is interesting. It does use 3D technology. Um, from a display perspective, it's really just an immersive 3-dimensional display, but there's a lot more to it than that. And of course, outside the scope of this program. So, because typically virtual reality is their game design and that kind of stuff. Where there's still not a lot of call for sort of live video virtual VR. We're getting there. Understand too that technology, if anyone's ever seen a 360 camera, so there's another one, there's a good example. 360 cameras were all the big rage a couple of years ago. People were buying them left, right, and center. And I read a review this morning, in fact, of the new, well, not the new, but the most recent GoPro 360 camera. And they're already saying, well, you know, the market's kind of fragmenting and people aren't buying them anymore. The problem with virtual reality is it requires a kind of a 3D presentation, which is difficult to do. There's a famous story of a woman who I think she produced a 3-dimensional film documentary, or was it a drama? I can't remember which. Anyway, at a beach, and she realized very quickly that she couldn't be anywhere in the shot. You couldn't be anywhere on the beach, so she buried herself in the sand because a 3D camera picks up everybody in all directions, right? So otherwise, it looks artificial because you realize right away, like when you watch, like I may have told you guys this already, when you watch The Bachelor, Survivor, all these shows, you're seeing two people, let's say The Bachelor, you're seeing two people having a dinner somewhere. What you don't see is the 30 people on the other side of the camera. And the audience doesn't care about that, but we professionals have to figure that out, right? So anyway, it's dry. I will try to make it as interesting as I can. The video, do we want to show video now? I don't know if I need to, you know what? I think I'm going to leave some of these videos for you guys to watch in the playlist. I don't need to go through every single one of them. The polarizing video explains how the light is actually redirected. So you can watch that. Let me just have a quick check and see what other videos are in that list that we should do. Because I know that this is probably, like I said, as exciting as watching paint dry. Oh yeah, so let's look at the backlighting. So let's do that. We will talk about then how the lights work in an LCD monitor. So I'm going to stop this, escape. All right, where's my playlist? There it is. So let's have a look at what's going on behind the screen. There we are. So this is kind of a, when you first see this image, it's kind of weird. So I'll try to explain as we go. Share, full size. So what's happening here is right now what we're seeing is we're looking at a monitor. They've taken, or the TV set, they've taken some of the plastic off around the front, the bezel and the like. So it's a bit exposed. What's happening in this image is it's hard to see because it's kind of dark. It's poor that it's, but nonetheless, all I could get is there's an image, you can see a little square and it travels across the screen, right? There it goes traveling across the screen. The rest of the screen is black, okay? So what's happening partly is that those LCD crystals are twisting back and forth to make this image move across the screen, right? But at the same time, there's a light behind them that's shining through. So they're twisting back and forth and allowing that light that's behind them to come through, right? So let's have a move forward to where the light is. So here's the light. So this is what's called local dimming. This is what sort of the latest deal they've done now with backlights. What these are called backlights, these lights, is that instead of in the old days, all these pixels would have been on all the time. Sorry, all these lights would have been on. These aren't pixels. All these lights would have been on. These are LEDs, in fact, I think, would have been on all the time, just constantly on, right? And that would have meant that you would have had poor contrast ratio because liquid crystals aren't perfectly black when they're on. So as a result, you get a little bit of leakage. So the solution was to have the backlight track the image. So as the image is going across the front of the screen, and we'll just cut back to that here, like this, the backlight is turning on and off behind the image. And that's what this is. This is called local dimming. It's a very common way to deal with the contrast. It helps the contrast ratio in the areas of the picture where the light is not on. Right? So here's the filter taken off, and now you can see the actual lights. So those are the LED lights. This is behind every LCD panel, every laptop probably, unless it's OLED. We'll talk about that in a bit. And there's the image again, okay? So that's what's going on behind the picture. So here's another image, not moving. And there's the backlight. So understand that if that light wasn't on, there'd be no picture because that light is what's making this image happen. The LCD panel is creating the pixels that form the image, but what's illuminating that image, what's creating that light to come at you is this light from behind, okay? So that's a backlight. Very common, very cheap, very reliable, but not the best, not the most perfect. And so again, one of the other reasons for learning this, and I'll just stop sharing this, is that you can kind of see where things came from.
Sony has developed a full-color flexible display built onto a sheet of plastic that can be bent but still show.
So let's talk about OLEDs because now I just heard from the OLED crowd. Let's go on to the presentation then. All right. So as I say, just understand where we come from and where we're going. Because if you can kind of figure out how TVs were made, you can also kind of start predicting what's going to work in the future. So, for example, 3D, you could sort of predict based on its method that it wasn't going to be the most successful thing. Anyone who saw a 3D movie realizes how dark the image is. So a quick sidebar for those who may not be aware. So 3D images generally are made by interlacing the fields, right? So field 1 is left eye, field 2 is right eye. So it's interlaced, which is great because we're using existing technology to, and then they have glasses that are synchronized. Glasses have a power in them, some of them. And so the glasses would actually blink at a certain frame rate to match the interlace of the screen. The problem is you're not only seeing half the image at a time. You're only seeing half a frame or half a frame interlace. Well, what does that mean? It means darker, right? Anybody who saw things like Avatar and other 3D movies noticed it was darker, especially if you took your glasses off during the presentation. You'll notice it was brighter with the glasses off because now you're seeing both fields together. but the glasses were allowing you only to see one at a time, right? So there was all kinds of reasons when you look at the technology, why it might not have been all that successful. It may come back. 3D's not dead. It's been come back at least 3 times since it was first developed in the 1950s. So you never know, it might come back again. Never say never in this business, that's for sure. All right, so LCDs, yeah, I've already talked about this. So inefficient because you're physically moving crystal, right? And inefficient because you have a backlight. So there's all kinds of energy loss. You've got slow write speed because that crystal takes a bit of time to get moving. And it's affected by temperature and sunlight because there's liquid in it. So it can freeze, it can soften. The sunlight can affect the reflection because there's a backlight. If the sunlight's brighter, anyone who's tried to use their laptop outside has witnessed this firsthand, or their phone outside. The sun comes in the front of the screen and washes out the backlight, right? And they're fragile. You break them, you can drop them and they break. Okay. DLP projectors, large screen, generates their own light. I already said this. Moving on. Okay, so OLEDs. So what are OLEDs? Let's just get to that. Oh, and quantum dot. We'll talk about that too. Let's get to that too later. All right. We talked about subpixels. I just put this in the presentation so you remember that every pixel is made up of 3. Every one of these pixels we're talking about is made up of 3 elements, R, G, and B. We talked about the sandwich. Just as a comparison between the 3 different sandwiches, you can see that LCDs have way more elements. The TFT LCD on the left, the OLED in the center has fewer elements to the sandwich because there's no backlight, right? The OLED is creating light from inside, right? The LCD, my cursor is really tiny. The LCD has a backlight element added as well as polarizers, and the OLED doesn't have the second polarizer. It only has 1. And then the micro LED has no polarizers, right? And even fewer layers. So simpler construction, but dastardly more expensive to make in the case of micro LED. Okay, so LCD, we talked about this, twisted crystals, polarizers. There's a color filter in front. So all the liquid crystal display pixels create white light because the backlight is white. So the white light comes through and then you get the color by putting literally a color plastic filter on the front. All right. Plasma TV, I'm going to skip them because we don't really use them anymore. I've got one. But plasma TVs basically created light with an electrical reaction with a gas, and were very fast, high contrast ratio. The only real problem with them was that they were heavy and they were expensive. But we'll skip plasmas because they're kind of passe. So there's a thing. So plasma, just we'll skip it, but also you'll notice the date on this slide is 2004. So somewhere around 2000, 2001, plasma TVs sort of came into their own, and by 2012, they were essentially dead in the market. Even though the technology is great, and this is what's weird. I've got one. It's a fantastic TV, but for whatever reasons, economic, manufacturing, whatever it was, they just decided that's it. We're not going to make these anymore, and they stopped making them. And that's what happens with our market. You can lose a good technology because someone's decided to stop making it, which is a drag. So OLEDs. OLEDs, I use the old electron in a hole, metaphor, Swiss cheese and olives. If you imagine the electrons are the olives and the holes are the Swiss cheese. When in an OLED, an electron drops into a hole, and the hole is created by the polarity of the material. It actually creates if you think of it as almost like a vacuum. The electrons are dropped into those holes. When that happens, they emit light. So the actual material that is made up from the OLEDs is made up by having something that will emit light when you apply power and have a surplus of electrons and they drop into the holes, light comes out, right? So electrons change energy from high to low. Energy can't be destroyed, so the remaining high energy that they had is released as light. And it's just that simple. And it's done with organic chemicals. These are things like fireflies and other insects and such that develop this technology. It's not really technology, develop this biology. We've just mimicked that using the same kinds of chemicals, right? The cross section of the OLED is you've got 2 glass transparent metal, let's try that again. 2 transparent electrical conductors, the cathode and the anode, on either side of the organic stack, which is the organic chemicals, and a glass sandwich on either side. And by powering up that pixel, the organic stack will generate light. And so there's no backlight. It's all happening from within the panel. Much simpler, much smaller, right? They're flexible because there's no backlight, because there's no rigid. So this is one of the reasons why these are important. There's no backlight, there's nothing rigid, there's no LED structure behind these. So you can basically print these organic chemicals on anything. And that's one of the ways they make OLED monitors, is to actually use a inkjet printer type device to spray these chemicals onto a surface and then apply the electrical conductors on either side. And now you've got a flexible surface, okay? I say latest in flat panel technology because the slide's a bit out of date. It's actually not the latest anymore, but it's still pretty new. So this basic slide, it's organic chemicals. One of the bad things about organic chemistry is that it degrades, right? We all get older, and organic chemicals break down the same way natural things break down. Oxidization, all kinds of things that would attack living cells, attack the organic chemicals, and they do degrade. So they have a limited lifetime. We still don't know what the lifetime of OLED panels is yet, but when this slide was first written a couple of years ago, I think it was 10 years. They weren't even sure because 10 years hadn't elapsed. So just a quick comparison again, the LED, organic LED versus the backlit on the left liquid crystal display, right? That extra material behind. So ignore the graphic on the left. It's just there to keep you amused. Really what's important about this slide is it's very promising technology. There's already small OLEDs, although larger ones are happening all the time. There is no size limit because it's a spray-on or chemical process. You could have basically any size monitor you could imagine, depending on what the manufacturing possibility is. They can be bent. So these phones that are going to have folding phones could have an OLED display because you can bend those. They have a large viewing angle and they're very high resolution. All right, but because they degrade, they're organic, they have their weaknesses. And here's again a quick idea of the sandwich structure. Just a quick, this is a quick terminology thing. The emissive layer is the one that creates light. The conductive layer, there's two of those, and they have the electricity. So you get the cathode and the anode and the conductive layers. And you've got the substrate, which is basically, the substrate is just whatever you've attached the chemicals to. Substrate is just a term that means like the base, right? So whatever you apply them to, it can be flexible, it can be rigid, it can be clear, you know. So you could have an organic monitor that's clear on both sides. That's the other thing with OLEDs, right? Because it's transparent, you could have a transparent substrate and a transparent top layer, and therefore be able to witness the monitor from both sides, which is kind of handy. And I've said all this, so I'm just not going to say it. So one of the options, one of the advantages to OLEDs is the high contrast ratio, because it makes its own light. When they're not making light, they're off, and when they're off, they're black, right? It's the pixels. So if you've got pixels that are off and black, you have a higher chance for a high contrast ratio. Wide color gamut, simpler than LCD. Low power consumption is important. The organic chemicals generate a lot of light. They're quite efficient compared to LCDs, because LCDs, one of the challenges with the backlight, of course, is that backlight generates heat as a byproduct. So that's inefficient. So you can see I'm focusing a lot on OLEDs with this presentation, because that was sort of the promising technology of the day. They have some issues still. They're faster than LCDs. They could be less than a tenth of a microsecond. Pardon me, a hundredth of a microsecond for refresh rates. For response rate, which is the pixel change, which means a refresh frequency of 100,000 hertz is possible, right? Whereas a LCD, so one of the things when you're buying LCDs is that generally the highest refresh rates are about 144 to maybe 240 hertz. Anything higher than that is done with tricks, and there's a video in the playlist from Linus about the tricks that they play to fake out higher refresh rates. All right. So that's enough about LEDs. I'll let you read the rest of this later. It's kind of just sort of technical stuff. Excuse me. Oh, we're getting close to the end here. Perfect. And we'll just cover the micro LED very quickly. So basically a micro LED is just a very tiny LED. They're not organic. Their lifespan isn't as short, so they'll last a long time. They're saying already 11 years of use. The challenge with micro LEDs is they're very efficient compared to LCDs, not as efficient as OLEDs. The challenge with them is right now they're really expensive to make. So what, I'm going to skip these and not read them all. I'll just show you the sandwich. The challenge is with the sandwich of the micro LED is that it's expensive to make. So what manufacturers are doing is they're kind of faking you out and saying, well, we've decided not to sell them as full-size TVs. We're going to sell them to you as interlocking panels, and you can make the TV you want as big as you want. Well, that sounds great, and it is kind of an interesting option. But what they're really saying is they can't make a micro LED TV that isn't going to cost $500,000. You know, so what they're doing instead is they're going to sell you like a little 10 by 10 panel, and you can build as many as you need. We'll see if the marketplace goes for that. It might have a great commercial application like for scoreboards and stuff and signage, but whether the average person at home is going to spend that kind of money to build their own television out of panels remains to be seen. Because I begin to realize I'm running on for time, here's a quick comparison of brightnesses and resolutions. Manufacturing costs, micro LED is very high. They got a very high resolution. They're relatively efficient, excellent color gamut. And we're going to sidebar with the nits. That's why I wanted to get to this before we finish. We'll spend the last 3 or 4 minutes on just measurements. So nits, what is a nit? A nit is a unit of measurement of luminance. It's the intensity of visual light on a screen. It's used to describe the brightness of liquid crystal displays. Most LCD displays are about 300 nits. Most LCD outdoor displays should be no less than 2000 nits to be visible. So obviously the more nits, the brighter the screen, right? A quick primer on the measurement units. Lumens. So here's where they get to fool you again when they market. Lumens are how much light comes from the source in all directions everywhere. So the backlight of an LCD monitor, the light's coming off the front and maybe the back and maybe the top. We're only going to see the light that's coming from to the front, right? So the lumens don't really tell you a lot. They're great for things like light bulbs and lamp fixtures, because in those cases, you want all the light that's coming out of the fixture. But in the case of things like screens, the lumens aren't as important as the candela, for example, or the nit, right? So be careful when you're comparing apples and oranges, when you're looking at specs, that you compare the correct things. So a lumen is how much light comes off in all directions overall from the light source. The candela measures the light in a specific direction. So basically the focus or target direction. So in the case of a light fixture, the candela would be the light coming forward through the front of the fixture, whereas the lumens would be all the light that's spilling off in all directions. That's the comparison. And the lux is how bright it's reflecting off your surface. So lux is always a reflected measurement. You would never say the light fixture has X number of lux, but you would say it would develop so many lux reflecting off another, like a face, for example, right? So when you measure light off someone's face, you're measuring lux, because you're measuring reflected light. Nits are area dependent. So one of the differences between nits and lumens is that nits measure 1 candela per square meter. So it's actually an area, a specific area, whereas a lumen is, like I said, all the light that comes off that light source from any direction, all right? Whether or not you can see that light, whether it's going off inside the cabinet or whatever, it doesn't matter. They count that for lumens.